Hello everybody and welcome to the beginning of page 24, and we are about to make kind of the main definition in our section here. Okay, so let's read the first part of this together. Let V be a vector space and let S be a subset of V. Okay, and we'd like to define what we mean by S being a linearly dependent set. Okay, here's what we want it to mean based on what we previously did. We'd like to think about linear dependence as saying that some of the vectors in our set depend on other vectors. Okay, recall that's kind of the question that we wrestled with on the previous page. So for example, just to refresh your memory here, we started with these four vectors, and we were able to demonstrate that U3 depended on the other three vectors. Okay, that kind of came out in this dependence relation that we came up with. And the question is, how did we arrive at that dependence relation? Well, our starting point was to take a linear combination of all four of the vectors and set it equal to the zero vector. And the key was, when we solved that system, we discovered that there are non-trivial solutions to it. That's what led us to this conclusion that there are dependencies in this set. Okay, so that kind of gives us a roadmap as to how we want to define linear dependence. So let's go back to our definition, okay, and read this together. So we say that S is linearly dependent if there exist distinct vectors u1 through un in S and scalars a1 through an, not all zero, that's the non-trivial part, such that this equation star is true. Okay, so we can kind of summarize this by saying, in other words, S is linearly dependent if there exists a non-trivial solution to equation star. Okay, and we want to make another definition. What would it mean then to say that a set is linearly independent? Okay, well, this definition tells us that it's the negation of linear dependence. Okay, a set is linearly independent if it's not linearly dependent. Okay, that kind of makes sense to define it that way, but what does it really mean when we say that S is linearly independent? It'd be nice to have kind of a picture in our mind of what we're saying there. Okay, so I'd like to add a note to this. Okay, we can get a definition for linear independence by just taking the definition of linear dependence and negating it. Okay, that's a bit of a challenge because it's kind of a complicated definition. Okay, so if we read the first line of the linear dependence definition, it says S is linearly dependent if there exist distinct vectors u1 through un and S. So if we want to negate that there exist is going to become a for every. Okay, so let's start our definition like this. S is linearly independent if for every u1 through un in S. Okay, and then we need to figure out how do we continue that. Okay, well, we're going to get linear dependence if there exists a non-trivial solution to equation star. Okay, we want to negate that, so we'd like to say something like, it's not the case that there exists a non-trivial solution to star. That's kind of confusing, but if it's not the case that there exists a non-trivial solution, what that's really saying is that the only solution to star is the trivial solution, where we make all of the a's equal to zero. That's how we're going to finish our statement. Okay, so equation star has only the trivial solution. Okay, so there's our definitions. And we will spend the rest of this section playing with those, seeing if we can come up with ways of demonstrating that sets are linearly dependent or independent, and then talk a little bit about some theorems that relate to these definitions.